Okay. That's the next lesson. Blast from the past, KJ? Where's Yemi today? Nobody knows? Oh yeah, of course. Capacitants and capacitors. Yeah, a bit like resistance and resistors. Yeah. Capacitants and capacitors. Okay. Yeah. Yep. All right. Right. So look at the following circuit here. In fact, I'll draw it again for you. There's a plate here. There's a plate here. You know, this could be something like copper. And then what you do is you put a battery around it like this. And the current goes along here. And when you do something like this, what you notice that happens is that this plate here becomes positive charge. And then this plate here becomes negatively charged. Okay? Which makes sense, doesn't it? Because here is the positive and here is the negative. But what's very interesting is if you take the battery away, so watch, look up, if I remove the battery and then close it, what will happen is this current will continue until all the charge is gone. So maybe for like half a second, this will continue to flow until all the charge is gone. So it's like we collected some of the charge and then released it. You know, we held some of the charge and then we released it. So when the current runs between the two plates, a charge builds up on the plates. If the cell is removed, the charge will release. Even though the cell is removed, a current will still flow for some time until all the charge is gone from the plates. Huh? Don't worry about that. In fact, it could just be a vacuum as well. So don't worry about this material. I don't even necessarily need you to draw this. You could just draw it the way I drew it here. Very simple diagram. This simple device, it's really simple. All it is two pieces of copper and you put them a fixed distance apart. When the current comes in, this will become positive and then this one will become negative. Okay? And then if you turn the battery off, this will start to release its charge for maybe 1 second. You got the idea? Yeah? So, huh? No, it's okay. I just want you to understand what is happening here. Okay, I'll go on. Yes? No, but I don't need a word for word.
I'm not writing a word.
Oh, it's a question, is it?
No, I'm just writing the idea.
Okay, but I need to go on.
Okay.
But, I mean, if you have a question, you can ask. This isn't a formal definition. Come on. Come on. No, I'm talking to my computer. Go to the next page. There we go. So this is the formal definition. A capacitor, also called a condenser, but you don't need to know that because it's an old term. A capacitor is an electronic device that stores electrical energy. That's all. So a capacitor stores electric energy. Okay? Now, capacitance is the ability of a body to store electric charge. A common device to do this is a capacitor. The unit for capacitance is the farad. Mathematically, the formula is C equals Q over V, where C is capacitance, Q is the charge, V is the voltage. 1 farad is 1 coulomb of charge per 1 volt. Yes? What's so funny? I'm not getting what's so funny. Am I missing something? It sounds like Fahad. Totally different. 1 F is 1 coulomb of charge per 1 volt. That is F equals 1 Q per V. Okay, so this definition you do need for the exam. Coulomb? What the heck? You're right, that should be C, not a V, Q. At the very end, guys, could you change that Q to C? That should be a C.
Small subject. Capital small subject.
Coulomb is a C. Unfortunately, capacitance is also a C.
But the coulomb is small c.
I think it's big, actually. You want to double check that. And it doesn't really matter because big C and small c look the same.
Yeah.
But when you write, like the symbols, you be careful. No?
Oh, you have to be, absolutely.
You cannot write amp small a.
No, and I'm saying you're right. Big C and small c are different, but they look the same.
But your c is just small c.
Your teacher might know, if your handwriting is neat enough. Okay. So, why do we care about capacitors? The reason is for things like this. Camera. But
Camera.
an old camera, you press the button and then you wait and then there's a flash. Okay? So what's happening here is when you press the button, the charge is getting bigger and bigger and bigger. And then after 10 seconds, then all the charge comes out at once. So you get lots of energy at once, the flash. I don't know, you probably don't have this, but maybe you've seen it before. You press the button and you have to wait. And then the charge builds up, builds up, builds up, builds up, and then the charge comes out. Okay? Here is something that you do know from TV. Here's another example. Yeah. So, charge builds up, And then, you know this one?
Yeah.
So this is another example of a capacitor. So these are why we use capacitors, to have a lot of energy at once. You build up the charge and release.
Just for people around today.
People who are about to die, yes, might be useful for them. Okay.
Or dial.
Huh? Or to die, yes. So look, here's an example of a question. I have a camera. When you press the button, it charges up until flash. The capacitance is 1500 microfarads and the voltage is 380. So let me draw that for you. So, whoops. Here is your capacitor, and the capacitance is, what did I say, 1500 microfarads, and then you have a voltage of 380 volts. So the current comes along, and then this charges. So my question is, how much charge is here? What's the Q? So the answer is, remember the formula, C equals Q over V. So that means Q equals CV, which will equal 1500 times 10 to the minus 6 times 380. What's that, please? .57. So 570 millicoulombs. Basic formula. Okay, can I go on? Yep. Right. So just like with resistors, let's have a look at the rules for when you combine them. So first I'll look at parallel. So for example, if this capacitor is C1 and this capacitor is C2, then what is the total capacitance if you combine them? And the answer here is C equals C1 plus C2. Now this seems a bit odd, doesn't it? Because for the resistor it was not this formula. What was it for resistors? 1 over R.
So I was 1 plus.
Huh?
Yeah, 1 over R.
1 over R, wasn't it? Yeah. Okay.
Which you do with I was I plus I2.
The I's, yes, in parallel add together, yeah. Now, if this has a charge of Q1 and this has a charge of Q2, the total charge is Q1 plus Q2 also.
And they won't be the same.
Yes, and the Q1 and the Q2 could be different as well. Likewise, the C's could be different as well. So I wrote these formulas down as bullet points here for you. C equals C1 plus C2. Oh yeah, and also don't forget the voltage here is the same as the voltage here. V2, programming error. Let's pretend we don't see that. V2, V1. So here the voltages are the same and the charge adds together. Right, so these are for parallel, please note. So capacitance adds according to that formula. Voltage is the same and charge is additive and different. Okay, shall we look at series now? Yes? So in series, it's like this. Capacitance capacitance. Alright, so what do you think the formula is for total capacitance? If you were to have a guess. It's the 1 over this time. 1 over C equals 1 over C1 plus 1 over C2. The voltage, V1 and V2, the same or different? Different. And let's say the charge here is Q1 and the charge here is Q2. What's the total charge?
1 over V.
No. Good guess though.
1 over Q, no, Q1 plus Q.
Good guess, but no.
Q2 minus Q1.
Nope.
Q1 minus Q2.
Nope.
Q2.
Nope.
Q multiply Q2.
Q1 multiplied? No.
No.
That's the last possibility left. Q total, believe it or not, is equal to Q1, which is also equal to Q2. So when they are in series, these are the same. And in fact, the total is also the same. This seems very strange. You feel like you should add them together, but you don't.
And the voltage here is not that.
But the voltage is different for each.
Yes, but they're added to, right?
The voltage adds together, yeah. So if you get the voltage here, it'll be V1 plus V2. Anyways, I put these in bullet points again for you. That's the total capacitance. The voltage adds and is different. The charge is constant. You got those? So we'll just have a look at one example and then we'll finish, okay? So let's have a look at an example. Can I go to the example? So I'll just draw it. It's 100 and 200 and they're connected in parallel. So let's draw that. So this is 100 and this is 200 milli. 100 milli. And the battery here is 10 volts. So my first question is to draw this, which I just did. Beautiful picture. My second question is to, calculate the total capacitance. What is the charge held in total, and what is the charge on each capacitor? Okay, so what formula do I use for my total C? It's C1 plus C2. So what is it here? 300 millifarads.
You say that.
No, I don't. Farad? Farads.
Yeah, that was like
Right. Well, we'll just have to change Fahad's name.
yeah.
Yeah? Right.
Call it that too. Okay.
Fahad 2s. Right. So remember, C equals Q over V. So what does Q equal? CV. So Q equals 300 times 10 to the minus 3 times 10. What's that now? That would be 3,000 times 10 to the minus 3. So that would be 3 coulombs. Isn't it?
Yeah.
Yep.
They are now series, right?
This is parallel. Now firstly, hang on, before we go on, this total charge is 3 coulombs. Are these the same or different charge? These charges are different. We need to calculate each charge. Let's do the first one. Q1 equals C1 V1. What's C1? What's C1? 100. Now what's the voltage here though? It's the same as the voltage here, isn't it?
Yeah.
Which is the same as
Yes.
10. So just multiply by 10 and here I'll get 1 coulomb. And then on the second calculation, Q2 equals C2 V2, which will be 200 times 10 to the minus 3 times, what's the voltage? 10 also again. So how much do we get? That's no surprise, is it? 1 coulomb, 2 coulombs, and the total is 3 coulombs. Okay, really quickly, let's put them in series now. Can I do that? Yep, alright. So, again, this is 100 milli, this is 200 milli, and the voltage is 10 volts. So really quick here, 1 over C equals 1 over 100 milli plus 1 over 200 milli. So that will be, how much is that? 3 over 200. Yes, so C equals 200 over 3 millifarads, which will be 66.7, we'll say, millifarads. So that's the total. Okay, now let's get the charge. Q equals CV, which will equal 66.7 times 10 to the minus 3 times 10, what's that? What is it? 0.667. Yeah? Coulombs. Now, that is the total charge of the two of them together. How much charge is on this one and how much charge is on this one? How much charge is on this one? The same, isn't it? 0.667 coulombs, 0.667 coulombs. The last thing I want to do here is calculate the voltages, I believe. Although I don't ask for it, I'm asking now. What's the voltage here? V1, and the voltage here, V2. So Q equals CV, V equals Q over C. So V1 equals 0.667 over 100 times 10 to the minus 3. So that would be 6.67. And then V2, you can do it the same way, and you'll get 3.33 volts. Now that's not surprising, because when I add the volts together, what do I get? If I add those two, should I get 10? Yeah, I should get 10. So there's no surprise there, okay? So, you know, this one again, it's like the simple circuits, same ideas, different formulas. In fact, the formulas aren't even that different. They're similar. They're practically the same. Alright, so then I'll put this up on Moodle later, the questions.